let's take a look at an example dealing with this angular kinematic stuff. So we're going to do 9.3 here. It says the angular velocity of a flywheel obeys the equation omega equals 2.75 plus 1.5 t squared, where t is in seconds. And the first part of this question says, well, what are the units of A and B if omega is in radians per second? So we just want to make sure we can find the units on these two coefficients. So the idea here is I know that I want units in radians per second. So that means I'm going to have to do something plus something, meaning these two things have to be in radians per second in order to get radians per second out. And so this one is just radians per second. However, this is kind of a pair, meaning that there's something times time squared, and time is in seconds squared. So something times seconds squared is going to give me radians per second. So that means it's going to be radians per second cubed, so that my second squared cancels out a second squared, so I'm left with radians per second. So those are the coefficients on those two values, so 2.75 radians per second and 1.5 radians per second cubed. Part B asks us, what is the angular acceleration of the wheel at 2 times, at 0 seconds and 5 seconds? So in order to find the angular acceleration, alpha, I'm going to have to take the derivative of my omega function. So my alpha is going to be 3t. Now those units still hold. I still have my coefficient as radians per second cubed, because radians per second cubed times seconds gives me radians per second squared. Now they want me to go ahead and evaluate that at 0, and I get 0. They also want me to evaluate it at 5, and so I get 15 radians per second squared in that case. Part C wants to know, through what angle does the flywheel turn during the first 2 seconds? Now, something I need to keep in mind here is this is not a constant angular acceleration. So I can't just go ahead and use the base kinematic equations like we did for some other problems. What we can do, though, is we can think back to how did we do regular motion? And so I could say, well, displacement, I could find displacement 2 ways. I could either take the final position minus the initial position. So I would need a theta function. So I could go ahead and create that. Or I can go ahead and say it's equal to the integral from time 1 to time 2 of my velocity function dt. That's the method I'm going to use here, because in order to get my x and my x naught, I would need to know where did it start. I could just choose it to start at 0, but let's go ahead and do the second one, because we can just math 9 that thing. So it says for the first 2 seconds, so similarly, delta theta is going to be the integral from t1 to t2 of my omega function dt. And so my delta theta here is going to be from 0 to 2 seconds of my omega function, which is 2.75 plus 1.5 t squared dt. Go ahead, put that in your calculator, math 9 it, and you'll come up with a delta theta, the number of radians it's turned through, the angle, the angular displacement, if you will, of 9.5 radians.